My name is Mahendra Tamrakar. Today I am going to walk you through an exciting and essential topic in computer graphics, color mapping and visualization. So let's continue. So here's the topic that we will be going to cover. So firstly, we'll know about actually what is actually the color mapping. So now color isn't just something pretty in graphics. It's a critical tool that helps us make sense of complex data. Color mapping is the process of transforming numerical or categorical data into visual colors. This technique is widely used in fields like scientific simulations, medical imaging, remote sensing, and even in your everyday apps and dashboards. So, so here the purpose and benefits of color mapping. So, uh, the question comes in your mind. That's why actually the color mapping is so useful. Why we need it. So, firstly, it enhances our ability to perceive and understand complex data sets visually, like patterns, outliers, and relationships become much clearer, and the use of appropriate colors. Secondly, it is widely used in user interfaces and dashboards, helping users interpret data intuitively, and color mapping works for both quantitative data like numbers and qualitative data like categories are and labels. So now let's talk about some common techniques. So starting with the grayscale mapping, this is perhaps the simplest form. It uses shades of gray to represent the data values. So here the lower values are usually the darker, closer to the black, and the higher values are lighter, towards the white. Like you seen, like you can see in the diagrams, the more the lighter value and towards the darker value. Here the lighter value means the higher values, and the darker values, the means the darker shades means the lower values. Here you see this in these things you see in these things in an X-ray images, black and white photography is simple but effective, especially when color isn't necessary. So next is gradient mapping, also called continuous mapping. Here, data values are smoothly mapped to a gradient of colors. This is common in heat maps. For instance, blue may represent low values, red indicates high values. It is widely used in simulations like weather maps or fluid dynamics, where you need to show gradual transitions. So then we have discrete mapping. This technique assigns clearly distinct colors to, uh, sorry for the disturbance. This third we are about this technique assigns clearly distinct colors. Each category value range. There are no blending here. Each color stands for a specific class, like green for forest, blue for water, and urban for gray areas in the satellite imagery. It's perfect for pie charts, political maps, or any categorical data. So now that we understand how data is mapped to colors, let's explore how colors themselves are defined. So this is where color models comes in. Now color models are mathematical representations that allow us to define and work with the colors systematically. Here we will cover the four major models: RGB, CMY, HSV, and YIQ. Here the YIQ is not present, but further we will learn about it. So, firstly, the RGB model, red, green, blue, is the most common in computer graphics. Here the components is red, green, and a blue. It is an additive color model, meaning we create colors by combining light. Each component ranges from 0 to 255, or from zero point 0.0 to 1.0 in normalized form. For example, let's see in a graph here, red is 1, comma 0, comma 0, green is 0, comma 1, comma 0, and blue 0, comma 0, comma 1. So when we mix red and green, we will get in yellow 1, comma 1, comma 0. And when we will mix red and blue, we will get magenta 1, comma 0, comma 1. So let's go further. Now the CMY model, cyan, magenta, yellow, is used in printing and is subtractive. Mm. Unlike RGB, this model works by absorbing light. Cyan absorbs red, magenta absorbs green, and yellow absorbs blue. When we mix them, when we mix them, here, cyan plus magenta, we will get blue. Magenta M plus Y yellow, we will get red, and cyan plus yellow, we will get green. However, mixing all three doesn't give us pure black. It gave us muddy brown like color. So we add K, black ink in CMYK for better contrast in printing. Here we have a formula for finding RGB when we have a CMY, like we have just subtract 1, 1, 1 from CMY, and for vice versa, CMY. We have to find CMY. So when we have to find CMY, we can find it through this formula, the matrix of 1 comma 3, 3 comma 1, as seen subtracting from the RGB colors. So let's go further. The HSV color model. Moving here, HSV in H stands for hue, S stands for saturation, and V stands for value. It's often used in design tools because it aligns more closely with how humans perceive color. Here, hue is the type of color, red, blue, green, measured in degrees on a color wheel, and saturation is the intensity of the color, and value is the brightness. As you can see, the angles that is making like a 360, is 60 yellow, green like 120, and this color 180, 240, and so on. Here, designers prefer this model because it's more intuitive compared to RGB or CMY. So, finally, we have the YIQ color model, which was used in analog television systems. Hereby stands for luminance, basically the grayscale version of the image, while I and Q carry color details. This model was designed so that the black and white TVs could still display part of the signal using just the Y component. It's mostly historical now, but it was crucial in early broadcasting. Here, like Y, just showing a gray. Here, I, which I and Q collectively carry the color details, like you can so see in the image here. So let's quickly compare these models. So here, RGB is additive and used in digital screens. CMYK is a subtractive and used in printings. And that's an HSV. It's perceptual and great for user interfaces and design. And YIQ was efficient for analog TV but is mostly outdated. So here each model has its own sense and is chosen based on their applications. There are further advantages, the primary use and limitations are given, which you can read it for afterwards. So here the summary. To wrap up, color mapping is a vital technique is when visualization. It helps us to translate raw data into something we can easily understand with our eyes. So we have explored different techniques, grayscale, gradient, and discrete mapping, and also discussed how color models like RGB, CMYK, HSV, and YIQ support these mappings. So here are the references that I have taken, the course notes and the lecture material, the Wikipedia posts, and the book Computer Graphics by Donald Hurd, and the Fundamentals of Computer Graphics by Peter Sterling. So thank you for the watching. I hope this lesson gave you a solid understanding of how color mapping works in a computer graphics and visualization.